Hi, I'm Robert, and today we're going to be talking about the Web Crypto API, or the cryptographic capabilities afforded to us by modern browsers. However, you might be asking yourself, first of all, why make a whole presentation about an API that's exhaustively documented on the Mozilla Developer Network? In fact, MDN has been an invaluable resource of documentation for me over the years. However, the Web Crypto API is a tough nut to crack because first of all, the error messages are not that friendly, which you're going to find out undoubtedly if you're working with Web Crypto API. And also, some data formats and parameters are non-obvious. So instead of providing you with a copy of the MDN site, I've decided to offer more of a cookbook for your different crypto needs. So we'll just run through several crypto stories on securing your data in transit and authenticating it by digital signatures. First of all, I'd like to say that this presentation is actually interactive. So all the code samples can be tried out in the browser because this presentation is actually in HTML. So if you'd like to visit the address presented here, and it's highly advisable because, the code samples are quite a handful. So just save this, or type it into your favorite device that you have with you, or at home, because all the code samples will be interactive. So basically, when you load this talk into your browser, there's going to be some predefined variables to help you out, and they also serve as a helpful starting framework for your first crypto project. So now. This also serves as a reference book to come back to. So if you're starting out and it's a quick reminder of some CLI commands or on some invocations that you might find hard, which are provided in a no batteries included fashion on MDN, then this is your site to go to. So without further ado, let's begin our talk about Web Crypto. Well, the cryptographic API is a security tool, first and foremost. What that means is it lives in an ecosystem that's composed of your environment and of the use cases. So let's talk about what security tools demand of you. First of all security tools, especially those concerning encryption, require you to use them correctly, which is what we're just learning now. Or otherwise, a tiny mistake can render the whole effort futile. So basically, pay attention, don't mistake the public key for the private key, etc. But that's perhaps the less profound of the points presented here. And the second point might be the more important one, and it's that the Web Crypto API doesn't live in a vacuum. So you have to consider the platform first, which is the web platform. Now, web applications are perhaps unique in the fashion they deliver code to the executor. That's because web apps have an innate property of always downloading the executable code to the browser. So, for instance, if you're installing a local app, from your distributions package manager or through an installer on your operating system, that means you get the executable code on your stable storage and can then, load it from a trusted store. And that's where the difference between web apps and mobile or native apps come into play. So in crypto, you usually have the prime problem of securing your encryption keys and your data in memory. But here, you also have to secure your application code delivery mechanism, which means you basically have to rely on HTTPS either way. And I will be understating this point all the time because it's just so important. The Web Crypto API is not there to replace HTTPS, it's to supplement it and to extend your crypto usage into new fields. So always remember that, first of all, your front-end application needs to be secure. And it cannot really be fixed with progressive web apps. even though progressive web apps download and store a local copy, they still refer to a refreshing mechanism that downloads a fresh copy every day or so. So, if someone gets a hold of your server files, then you're still toast. Okay, so the second major use of crypto is securing data in transmission, which basically means two things. First of all, ensuring their integrity so that they're not corrupted. And secondly, making them secret, which is typically called encrypting them. So, but also a third area of usage for web crypto APIs is storing the data. And as we'll see in a second, this is actually quite useful. So now we can use web crypto quite effectively to deploy new kinds of applications which provide end-to-end security, because TLS and HTTPS only provide us with client-to-server security, which is simply not good enough for some private communication scenarios. But also, quite interestingly, it can free us from having to rely on the security of our cloud platform. So assume, for example, that we're hosting our front-end application ourselves, but decide to delegate our storage to Amazon S3 or a competitor. So basically, then we would normally have to trust the cloud provider. But we might be fine with it. But our clients, who are pretty demanding when it comes to their security needs, might not be willing to make the same trade-off. So, using Web Crypto API and securing the data ourselves on the front end, we can basically alleviate that concern. And last but not least, if you're writing something along the lines of a password manager, for instance, then it's your prime responsibility to secure the data at rest. So the last thing you want to be doing is storing your customers' passwords in plain text, and this also can refer to personal data or PII according to GDPR. So you get the idea. However, let me restate once again that you should never aim to replace HTTPS for two reasons. First of all, it's still necessary to guarantee a secure delivery of your application code to the front end. And secondly, but perhaps more importantly, is you shouldn't do it because HTTPS and TLS are mature protocols, unlike the things we're going to invent in a second. And now for the more interesting part. We'll start with implementing a simple message flow with sending a message to a recipient using a public key infrastructure. To actually use any kind of asymmetric encryption, we first need some keys. And if you've ever dealt with any crypto stuff involving public and private keys, you've probably done the steps that are outlined here. Now, this is pretty standard, and if you Google for generate public and private key, this is probably the first thing that's going to pop up on Google. But I'd like to point your attention to the third step. So OpenSSL by default generates one private key, and then we have a command to derive a public key from it. And you might be thinking that the PEM format should be okay, because web crypto, as we're going to see in a second, consumes PEM, consumes DAR files, which are actually encoded in the PEM format. However, this is not the case, it turns out, and OpenSSL actually does produce PEM files, but it's not PKCS #8. It's not the correct format, though it's really indistinguishable. So whenever you get weird errors like invalid data or something like, I told you that they are not particularly helpful with Web Crypto API. Whenever you get some weird errors, remember to check if your key is really PKCS8. So if you haven't skipped the third step. Sorry, it's a really dry topic, Right, so first of all, to encrypt a message using PKI, we obviously need the public key of the recipient. And with the web platform, but also with any platform, to be fair, we first need to get the public key from somewhere. And actually, key exchange is the harder part of modern cryptography, because we've got all the algorithms implemented. We can mostly assume they're implemented correctly. Most consumer programs are in browser, etc. But how do we know we've got the correct public key? This is unfortunately outside the scope of this talk, but let me say that the key exchange server, or where we get the public key of the recipient from, is equally as important, or perhaps even more important, because it's often overlooked, as the encryption process itself. Now, when you've got the public key of the recipient, it's time to encrypt, which covers the entire next slide. And then we take the message and send it to the recipient. However, how does the recipient know we were actually supposed to send him this message? Or how does he verify the legitimacy of the message? This can be done twofold. For some applications, it's not actually necessary to ascertain the veracity of the message cryptographically. It's often enough to rely on the platform itself. So we can infer that if someone sent this message here, like if he saved it to S3 or something, he probably had the authorization to do that, so the message itself is probably okay. And this is mostly useful when you're protecting the security, the secrecy of the data. So it's a useful assumption when, for example, you're protecting files like PDFs uploaded from the client to the server, and if secrecy is all that matters, then this is probably enough for you. However, if you're sending something like commands from the client to the server, and you really the processing of an invalid command could have serious consequences, then you'd better sign the message, which is the last part of today's presentation. We're gonna get to that soon. And now the code. All right, this is roughly the same thing that MDN tells you, but I've split it to 3 steps so that this is more clear. On MDN, it's the implementations are there, so I hope this is more clear than most examples we find online, because you have to do 3 things. First of all, since our keys are usually in the PEM format, which is a textual format, dash 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 begin public key dash dash dash, and then the base 64 stuff. Well, basically, you have to decode it into a binary format. So what we do first is call the an extractor function. It's not a built-in function. It's just my own implementation, but it's the same thing that's on MDN in all examples. So if you just find any web crypto examples at all, it's the same function that decodes unpacks the part between the begin and end. Then base 64 decodes it and turns it into an array buffer. Okay, so we'll be dealing a lot with array buffers today. So what we do is call import key first to get a handle or a crypto key object. And this is what import key returns. Actually, it returns a promise, so we have to use await or then the promise operators for asynchronous operations in JavaScript. So then when we've got the public key object, we can use it as a parameter to encrypt. We just pass the object itself and pass some parameters. Here we're using the RSA asymmetric encryption scheme with OAEP, which is sounds like a difficult abbreviation, but it actually stands for optimal asymmetric encryption padding. Well, it's quite unimportant, but it's the only algorithm that the browser offers in when it comes to asymmetric encryption. So here you'll notice that we have to encode somehow the plain text. So we're passing a string to text encoder, which is a built-in interface of the browser, and that basically spits out an array buffer. So we're always operating on binary data. Okay, any questions so far regarding this slide? Okay, so it's just 3 steps. Decode the key, import it, and then use it to encrypt. Simple, right? Now, receiving and decrypting messages is quite unsurprising. What we need to do is load our own private key, but this proves to be challenging with web applications, For one simple reason. We have to store the key somewhere, and if this were several applications such as a Node.js daemon or something, then we would have the comfort of a local file system, and we could load the key from local storage. Well, turns out browsers nowadays also have facilities called local storage. However, there's a slight problem with it. Assume for a moment that you have your key loaded into local storage, so it's persisted. You can basically get it on the front end. However, if your web applications suffers a breach, or perhaps a cross-site scripting issue where someone injects malicious JavaScript code into your application, then same origin policy applies. And since it's the same domain, like it was injected into your website, then they can recover the private key easily. So yeah, it's a vulnerability, and it's actually a reason why I don't recommend writing if you don't have to web-based password managers, just because of this cross-site scripting vulnerability. I mean, it's doable, but it's not exactly the same level of security that the local apps afford. So obviously, when we've got the private key loaded from hopefully some secure storage, then we reverse the operation. So we import the key, decrypt using it. It's nothing surprising, right? And then, depending on our security requirements, we should check the authorization, like the signature of the message, which is not included in this tiny slide here. So yeah, basically it looks the same, but obviously this time we're extracting the private key. We need to pass the PKCS8 format, and this is the important part, because if you forget to convert your OpenSSL key to this format, then you will get really weird errors. So I've underlined it here. So if you refer back to this presentation, it will be underlined on like every slide that uses it. And obviously we get so this plain text that we get is an array buffer, so we have to decode it to get a string. Now we can do the same thing in the CLI if we've got OpenSSL installed, which we presumably do because we just used it like 3 slides back. So I've included the slide here for future reference because, well, most examples online refer you to a command called OpenSSL RSA util, which is evidently wrong for this usage. But the top, like all the results on the first page of Google, will point you to RSA util, which doesn't work with OAEP because it's a fairly new cipher. So just to keep in mind, use the new non-deprecated subcommand, which is called public key util or private key util. I'm not even sure what this stands for, but it's the new usage. So just just make sure to check back if you're at a loss. Now there's a fault that I didn't mention on the previous slide, and we'll get back to that in a second. All right, so our previous asymmetric encryption attempt had one major flaw, and that's we can't really encrypt or decrypt anything that's bigger than the key size in the algorithm using these algorithms. So, for instance, assume we're using RSA 4096. All right. I think this must be the third one today. Okay. Must be the NSA. Well, so the flaw the asymmetric encryption attempt suffered from was that you can't process any message that's bigger than the key size. So, for instance, if we're using RSA 4096, we only have 4096 bits or 512 bytes for our disposal. So that doesn't make for a very big message. I mean, honestly, you can't encrypt any image with it, or Well, usually not even a simple JSON string if it contains more than 2 or 3 fields. So basically, it's going to be problematic. And for this reason, a technique called key wrapping exists, because we've also got block ciphers such as AES, which is the Advanced Encryption Standard, at our disposal, which can encrypt arbitrary sized payloads. So it's called block encryption, and basically it does by chaining blocks. So it takes the first block, appends the second block, which uses the information from the previous block. Well, the important point for us is it can use arbitrary sized inputs. So it will most of the time we'll actually be using key wrapping for big messages or for medium messages, which basically covers 99% of our usage. So to use key wrapping, first we have to generate an encryption key for our symmetric encryption. The way symmetric encryption works is by using the same key for encryption and decryption. So obviously we can't share it with the world, because that would render our encryption void. So what we do is we generate a symmetric or one-time use encryption key. We also need to generate some other parameter called the initialization vector, and it's unimportant what it does, but what matters is it needs to be unique for each message exchange. So you have to regenerate it every time. So then you encrypt the message with the symmetric cipher, which lets you encrypt arbitrary sized payloads. And then you also have to encrypt the encryption key, the message encryption key itself, using asymmetric encryption. So you're keeping this way you're keeping the message encryption key secret, and you're exchanging the message, the key, and the IV, because you also have to send that in plain text to the recipient. So we're going to see how that works. It's a little more involved, so I've split this into 2 slides, but it's not going to take much to follow this code. So now we have to, first of all, we have to generate the encryption key, which only takes like 3 parameters. We need to make it extractable. So this parameter here, we've been passing false all the time, and that made the key unavailable for exporting or key wrapping. So if we deleted, the original variable from our memory, then the key would be inaccessible to JavaScript. Now we have to pass true here, because we will be exporting it or sending it to the other party, right? So it has to be extractable. And of course, it's only used for encrypting the message. So what we do next is we need the IV for successful and secure symmetric encryption. We can't, just use math random, so we use crypto.random values, which is supposedly secure. And what we do is, quite unsurprisingly, we use the ASGCM, which stands for Galois counter mode. It's a bit more on that later. We use a symmetric cipher to encrypt the message key, not the message, but we encrypt the message itself with the message key. And on the next slide, we encrypt the message key to send with the message. So now we've got one crypto text, which is the message itself. This is the bigger one. And we also need a wrapping key. So we will reuse the key from the previous slides, which is the asymmetric encryption key, the public key of the recipient, remember? So we actually applied the same parameters, but previously we were passing encrypt here. Now we need to pass a different string for usage, or otherwise the browser wouldn't let us call the next invocation, which is wrap key. And we'll be using this key for securing another key. So we come up with the wrap message key, which is the encrypted per message single-use key. And we send the whole triple. So the wrapped key, which is encrypted, the encrypted message, and the IV to the recipient. And now we're going to see the whole process in reverse, which is decoding the message or decrypting the message on the recipient's side. So quite unsurprisingly, this consists of getting the private key. This time we're not decrypting, we're using it for unwrapping. So it's basically the same under the hood, okay? But the browser actually needs you to specify these explicitly so that you don't shoot yourself in the foot. I think it's intentional and quite a welcome addition to the standard. So now we need to recover the message key first that we will use for decrypting. So, okay, I think this is the most complicated call of all, because it needs to be given the encrypted wrapped message key, the decryption key for the message key, and it still doesn't give us the whole message. So we get the key back. So these are the parameters for the wrapping key. This is a parameter for the wrapped key. And what this does is also offer us a crypto key object. So this is the key handle that we can use to finally get our message back, which we do. So this is actually two steps. One is unwrap key, and we get the plain text, the final plain text, by calling decrypt with the unwrapped message key. Like, what could be simpler, right? And obviously, we also get an array buffer, so we also need to decode it if we're to do anything with it. Now, we might also want to use the same technique to send stuff securely from your client to a Node.js server. And please don't read all this code right now. It's here for posterity, for future reference, if you decide to go back to this presentation. But just focus on the first two rows of the code. Like this stuff here is necessary when you're using AS with the GCM mode, and this is actually a good and a common encryption scheme. What Web Crypto API does for you under the hood is actually concatenate the outputs of the encryption function, because the encryption function actually produces more than just the encrypted or the crypto text. It actually produces the crypto text plus an authentication tag. Now this is important because the Galua counter mode for AS encryption standard actually also involves a check, let's call it a checksum. It's actually an authentication tag that makes sure that your message was not tampered with. So you can actually verify, and this verification is here. Verify that the message has not been altered. So this means the encryption is non-malleable. You can't, alter some bits and get garbage on the output in transit, because it will be detected. So it's like applying a checksum, like an HMAC on your message. So it's actually pretty useful. However, by default, Web Crypto API will actually concatenate the two, so you get a large buffer with the crypto text and the tag. So if you're decrypting in Node.js, and this took me a while to find out, you actually have to split the buffer. So you take the last 16 bytes, or whatever you said, but the default is always 16 bytes, and you have to, just pass the crypto text for decryption and unwrapping and stuff, and then you have to process the tag separately. So that's probably not important right now, but if you do decide to use this with Node.js, this slide will, it will be worth its salt. And now, let's get to the last part, which is signing or authenticating your messages. You'll often need to prove that the message was actually, I would say sent, but it's not a good word, that the message was approved or generated by some entity that is in possession of a private key. And this is called signing, and the other party will be the verifying party. So what we do in public key infrastructures is use the private key, which we're reporting here again in the PKCS8 non-default format. We'll be using the RSA PSS, which is an encryption format with some random padding to secure us against padding attacks. And basically, we also need to indicate that we'll be using it for signing, which is, you probably get the idea by now. So obviously, you need to, encode the data to sign, and then you get the text signature. Now, when we were encrypting, we were getting the ciphertext on the output. Now we just get the signature. So the signature can be verified, but you still need to send the original text, because it does a digest in the background. So you're actually sending a signed hash, which is in this case SHA 256. So you still need to send the crypto text along with the signature, right? So you need the two to compare the digest to the plain text. So verifying is quite intuitive as well. And yeah, we use the public key for this because it can be, the key is publicly available and it can be used to check the veracity of the message. However, there's a slight problem when using encryption and authentication, which I'm going to describe in a minute. So obviously we get this check, like this is a boolean that indicates if the message passed the authentication check, the signature check, or not. So you might be tempted to roll your own equivalent of HTTPS, which basically includes secrecy of the message and authentication to make sure that the message was not tampered with and was generated by the trusted party. However, this comes with a certain risk. And it's actually implemented wrong in most protocols, but quite mistakenly, I mean, quite accidentally, they work correctly just because their payloads match what's being sent. But, well, the vulnerability is actually a pretty obscure one, and it's not widely known in the field, which is why I'm including it here. It's called surreptitious forwarding. I hope I'm pronouncing this right, but basically it means stealth forwarding. Okay, assume, well, we'll use the usual suspects, which is Alice, Bob, and Charlie, obviously. So, assume Alice signs and encrypts a message saying, Alice said this and this, and the message basically says you're fired. Okay, Alice is the HR manager or something, and she basically is tasked with firing Bob today. However, the message just says you're fired. So Bob receives this with Alice's signature. It's signed and encrypted, right? So he peels off the outermost layer, and he can, because it's encrypted using his public key, so he can decrypt it. And then he's left with a signed message by Alice saying you're fired. But, well, who's fired? When he takes the message and forwards it to Charlie, leaves the building with a sad frown on his face, and it's no good. So basically, this is actually a mind-bogglingly simple vulnerability in most internet protocols, and it's not addressed in PGP. It's not addressed in XML in XML digital signatures, and basically anywhere. So when doing this, first of all, you should really get a copy of this presentation and click this link, because it includes an important, it's a long article, but it's written really clearly. So basically follow this, and okay, that was too soon. Sorry. So basically, the article describes how you can prevent this, and well, the fix is actually pretty simple. Because if you prepend or append the intended recipient's name to the message, like if the message said instead "message to Bob, you're fired," and you sign this, then, well, it becomes a non-issue. So it's like a very simple solution to a complex technical problem. So read the article, because it's not the whole story. There's also some cryptographic vulnerabilities in there, which are unrelated to this. But yeah, basically, if you're doing both signatures and encryption, make sure to at least include the recipient's name to prevent this social attack, because it's not a cryptographic attack. I mean, at least this variant that I have just described, it's a social attack. So just prevent this in your crypto systems, please. So takeaway for today is, first of all, know when to use web crypto. So don't replace HTTPS with it, supplement it, and take care about your web application's code delivery security. Or better yet, use it mostly with already delivered applications like desktop applications, Electron. You know the drill. Well, when using symmetric encryption with key wrapping, which is basically always, just use a unique IV that's generated securely. And then when encrypting and signing, just read the paper and prevent social attacks. And well, for today, that's the formal part. And now's the time for questions. Yep.
Piotr?
Do we have a mic? Okay.
So my question is, as with most web APIs, you get this problem where you want to test it in Node.js, and then you have to like import isomorphic fetch and all of this other stuff. How well supported is the Web Crypto API on the Node side? And have you written any tests for it that run in Node?
Okay, so we have actually used the Web Crypto API in Node.js because a library demanded it, and there are some wrappers. And I'm not actually worried about the level of support because, polyfills exist, and Node.js actually, has its own crypto layer, which is, an example of this is here. So it's fully functional, but the issue is it's different, right? It's a completely different API. So there are some adapter APIs, and they work rather well. For instance, I think Peculiar Ventures has a wrapper on NPM, and it's actually pretty useful. About tests, there is a test suite that covers it. So basically, we've been using it in an XML scenario, which is actually pretty sad. But yeah, it basically passes, the higher level test with XML pretty well. So if you need a wrapper for, to unify the browser side and the Node side APIs, it's there.
Second question,
another question?
And another then.
Hello, I'm Michael.
Hi.
Thank you for the presentation. I would like to ask you, you said that you were using this crypto API in practice.
Yeah.
And did you use it for browser-to-browser communication? And if so, how did you handle this private and public key, entity in the browser? Because
You mean key exchange or storage?
Yes. How did you handle this? One user has the private key and the other has the public one.
Okay, so first of all, I did plan on and did come up with a proof of concept software that would use the Web Crypto API, and this is actually how the idea for the talk was born. But this was actually a different scenario. It wasn't between browser users, but it was a user of a client sending some data files to a device that's located elsewhere. So basically, I had a device with Node.js. Running and doing basically this. I mean, I copied this off this project straight out of the code. So I have some devices which need to receive documents sent from the browser, but I distrust the cloud platforms that's in the middle. So I put the data on Amazon, but they don't do the encryption. We do. So the front end actually has the encryption key. The back end, which is located somewhere, does the decryption, and the platform in the middle is oblivious. And this is, I think, the most interesting use case. I haven't still come up with a useful use case for browser-to-browser communications where both sides are actually delivered to the client by the browser. However, one other interesting use case is web password managers, which are obviously not perfect because it would be much better to have both the code and the keys stored locally. However, at work we use a commercial password manager product that actually uses this API, or polyfills were not available. So it does work, and it affords you the ability to actually handle the keys in your browser. So the server doesn't actually have the passwords or do password encryption and decryption. So it's actually a perfect use case for keeping the middleman or the cloud platform oblivious of your data, of your customers' data, and for doing sensitive data handling on the front end. However, when it comes to the case that you mentioned, which is cross-browser communications, we already do have, we have to trust someone, and that's the key distribution server. So we can, just as well do WebRTC through a, middleman, just use the established protocols such as HTTPS, and basically, be done with it for most scenarios.
Okay, so I think that was the last question. Yeah. Okay. Thank you very much for your answers, and thank you for the talk. Congratulations.